And it like wasn't that warm.
Hey everyone! Welcome to Interest coming despite the focus on Ophelia.
Yeah.
So again, for everyone that just came in, please scan this QR code so that we know that you guys came and we can keep track of who has came to the lectures. And okay, I'll put a switch this.
Alex. Peter. Could have been a lot of places.
That's the long more than we expected. Hello to everyone on Zoom, and hello to everyone that just arrived. So again, please use campus groups to scan this QR code, so we know that you guys just came to the lecture. And if you're ready, just let us know, and we can just jump straight to the content of the lecture today. Hello, please scan the QR code using campus groups. Everyone done scanning? Everyone on Zoom done scanning? Done? Okay, I'm gonna send the okay. Okay, great. So we're just getting get straight started into the content of the lecture today. So today we're gonna give for you that just came in, we're gonna show you the check-in QR code afterwards, so that we know that you came. Great. So welcome everyone. Thank you again for your interest. That's again a lot more people than we expected from the beginning. So today's lecture is going to cover some basic concepts and fundamental understandings to brain-computer interfacing, basic neurophysiology, etc., etc. So without further ado, perhaps then you're presenting the general framework of why we're doing this lecture.
Yeah, so thank you so much for coming out. I know it's raining, and I know you guys are all pretty excited. So the goal of this kind of lecture is to kind of give a basic overview about brain-computer interfaces. Now, this isn't going to just touch on some of the basics, and I'll kind of walk through how the general framework of a brain-computer interface works. And this is supposed to be a relatively chill environment, so feel free to ask questions when they come up. And yeah, so the first, of course, first step in a brain-computer interface is recording from the brain. And so there's a few brain regions in particular that we look at when it comes to brain-computer interfaces. One of them is the motor cortex, and we'll touch on that in a later slide. But after you pick the particular brain regions you want to record from, there's various recording technologies, and those can range from invasive neurotechnologies, which include which need surgery to implant the recording device, and non-invasive, so things that don't require surgery. So after you record all the brain signals, the next step is you have all this data, you need to extract certain features from it, and after you extract certain features, you can use algorithms to detect the user intention from a particular neural data. And then that neural intention can be used to control some sort of machine effector, like a robotic arm, a drone, and whatnot. And there can also be feedback. And so in the very last slide of this presentation, we'll show an example of APL, Johns Hopkins APL. They recently added a feature to detect heat using a prosthetic arm. And so that's a method of like feedback. And so we'll kind of run through all this, but this is kind of like the map of what we're going to go over. And so I'm going to talk about the neurophysiology behind brain-computer interfaces.
Great. So, well, boy, good. So now we're going to cover some very basic neurophysiology. which is very important as, again, this is my personal belief, but I think everyone should believe it. As engineers, it is very important to understand basic mechanisms, so you have a good idea about what you're gonna do using the knowledge that's stemming from your basic understanding of basic mechanisms. Feel free to say this to chair.
And there's also a chart.
It's a chair. Yeah, on the back. Great. So first of all, back to the most fundamental component of a brain and nervous system, the neuron. It is, as we say, the basic unit of neural control and processing. So for the canonical, that is the most commonly agreed neural structure. Most neurons have dendrites, that's all of these tree-like or root-like branches outwards. They have a cell body, that's where like all of the jazz is going on. And this very long single extension, that's the axon. Real neurons may not always be the canonical neuron. They can have whatever kinds of shapes and sizes. But for our understanding of now, just keep in mind, the dendrites are the input. So a neuron can have multiple inputs. The cell body collects all of the inputs from the dendrites and somehow sums it up and processes it in whatever way. And then after you reach a certain threshold, the signal is sent out through the axon as output. So simple. So for those of you that are interested in computer science, you may have heard of neural networks. That is, the neural networks is literally a model of the nervous system in a way that they would use these, probably we would call them parameters, but what they actually are is they would have weighted input, some kind of activation function, and an output. It literally corresponds to the dendrites, cell body, axon, and synapses. So there's a physiological background towards how neural networks are designed. But a neuron is not just about math. A neuron is a kind of, a cell, you can consider it as, a neuron is a cell, first of all. And cells are mostly, they are electrical chemical machines that process everything. So signals can be so in the neuron, signals are transmitted in both electrical and biochemical ways. For example, so what this GIF is showing is how the signal is being transferred along the axon. So this is along the cell membrane, and just by local changes of ions coming in and out, this is showing a voltage being passed down the axon. So an axon, again, is not a copper wire. An axon is where, so there are no charged particles going down the axon. Instead, they travel across the cell membranes, and what's actually being passed down is a voltage spike travels down the axon. That's the electrical way that signal is being transferred along the nervous system. And this is the biochemical side of it. Of course, there are these ions you can care about, but also, what's more importantly, at the connection terminals between cells, between neurons that are synapses, electrical signal would trigger voltage-gated calcium ion channels to stimulate the release of neurotransmitters to a synaptic cleft. So at the synapse that is in between neurons, signal is being carried forward in a biochemical way. So signals are passed both in electrical and chemical ways. And next slide, we're gonna go to a very overview. Just first we cover the basic units. Now we just go to the whole brain. And
So most of you guys already know this, but we're gonna review it. So you have the frontal lobe, the temporal lobe, the parietal lobe, and the occipital lobe. And the frontal lobe contains the prefrontal cortex and the motor areas. So essentially, you have the central sulcus here, and the precentral gyrus, that's the motor areas. And then the postcentral gyrus, the somatosensory cortex. Then you have the temporal lobe and the parietal lobe. Temporal lobe is the auditory cortex mainly, among other stuff. And there's been a lot of work done in terms of BCIs with the temporal lobe and auditory cortex. Then we have the parietal lobe and the occipital lobe. Somatosensory cortex is very interesting. And then in V1, the primary visual cortex, we have simple cells and complex cells. When we look at simple cells before, we've been able to figure it out somewhat, and especially like how like they fire when you have a specific like sort of stimulus in your visual field, like let's say like a square object going downward or something. And then complex cells, they fire to much more complex stimuli.
So that is a fly over all of the brain regions. You don't have to remember all of it now. We're going to cover more in detail as we actually go over, like work on products that relate to those different regions. But the general gist of it is that for BCI purposes, we mostly care about the sensory motor cortex because that's one of the best understood cortices, and also the occipital lobe, where studies of it has, where that is where the primary visual cortex is. That is because we also have very well understandings of how the neurons there encode visual information. Right. So across all brain regions, how are the signals generated? So there are a lot of complexities involved, and like we are still working our ways through understanding them. The field of science that studies it called systems neuroscience, but that is a different topic. So we're not going to go too in depth. What you guys should know is that neurons sometimes fire together, or they do not fire together. So we call them neurosynchronization. That is when all neurons or a group of neurons are firing together at a certain period, or they can be desynchronized. That is just neurons firing sparsely on their own. Those are general phenomena that's being observed across brain regions. And these two events, they happen depending on what exactly your brain is doing. So synchronization, that is when neurons are firing together, they create very strong electromagnetic signals, because when you think about it, when each neuron fires, there's a local change in the electrical potential in the area. When the neurons are synchronized, that is, with all of them, with a couple of them are both causing that same local field potential change, or are all causing that electrical potential change. That is, in that region, they're going to have a more pronounced change in the electrical potential. So those signals, they can be more pronounced and easier to be picked up by, say, the EEG headset, for example. So those are the signals that typically that's being sought for, at least with the current understanding of technology. So without further ado, let's get to this. So by the basic understanding of neurosynchronization and desynchronization, just for the sake of using EEG, there's this headset that goes onto your head over the skull. There are some common frequency domains that we care about. So frequency being at what rate the neurons are firing together. So there's a delta wave that's less, like a bit less than 4 hertz, 4 times per second. That's usually related when you sleep. There's a theta wave that's from 47 hertz. That's when you're in a sleep or deep meditative state. And the alpha wave, like higher frequencies, 8 to 12 hertz is calm wakefulness. Then the beta wave, 12 to 30 hertz, normal cognitive processes, and the gamma wave that's greater than 30 hertz has high degree of concentration. So intuitively, this makes sense. I hope it does, because when you really think about it, the faster you're processing information, the quicker your neurons have to fire. And the more likely it's going to be for clusters of neurons to be firing together at higher frequencies. Therefore, you can observe such waves on an EEG graph. Does that make sense? I need more explaining. Okay, great. We go to the next part.
Awesome. So that was all of the neurophysiological and neurorecording things. Now we want to move on to kind of signals. And so,
okay. I'll go over this again, some very basic understandings. So if you forget everything about basic neurophysiology, you should remember how the neuron works, because if you understand how the neuron works, you can have a better, you can then deduce from that to understand how the entire nervous system works. Okay, because the nervous system is literally just neurons connected. And then, as to from an engineering perspective, we want to understand how do you want to stimulate or record neural activity. Again, back to the neuron. Recall that signals, neural signals, they transmit both electrically and biochemically. Where's the electrical part? You guys still remember?
Voltage when the ions.
Where is that voltage at?
Axons.
The axons. Great. They're also in the cell body, but just generally, as a rule of thumb, inside the cells, they're passing mostly in electrical waves. Where does the chemical wave happen? Where are the synapses? What are synapses? Where the neurons connect with each other. Great. So, neural signals transmit both electrically and chemically. That means we can also measure these signals both electrically and chemically. We can also intervene with the signals both electrically and chemically. So, most commonly, at least what all of this here is doing is that they would collect those signals electrically. And that's also what's being mostly commonly done in the field of brain-computer interface. So what you do is you literally just plug electrode. Electrode is literally just a conducting wire, nothing fancy. Or it can be a very high quality conducting wire, whatever. But you just stick that electrode near a neuron or near some neural tissue. It can be non-invasive, it can be over your skull. It can be deeper, invasive, it can be plugged right into your brain. But it's literally just a conducting wire that's being placed near a neuron to pick up either voltage or current that is generated. So I've emphasized on voltage here because there's some very basic high school physics. I hope everyone took physics in high school. So for this diagram, this thing just consider as whatever kind of signal source. So imagine a neuron is generating a whatever signal. Okay, so can anyone tell me how do you use a voltmeter to measure voltage? How do you use a voltmeter to measure voltage? To measure voltage.
You measure 2 points.
That is okay. So if you connect 2 points, what are you measuring? Where are you measuring the voltage?
The difference.
The difference? Okay. So say I want to get the voltage of this node, or I want to measure a voltage at this node. The example here is showing that I'm using a voltmeter to plug one end to that node and the other end to ground, so that I can know, okay, this is the voltage of this node. So measuring voltage is relatively simple because with devices, or at least brain-computer interfaces, we usually adopt a common ground. That is, it can be somewhere that's generally signal agnostic. For example, it can be the elbow, it can be at the base of your head, at the skull. So that is usually the common ground level, and then you can just plug the next electrode at whatever place you want to get the voltage from that place. However, if you want to measure current, can anyone tell me how to use an ammeter to measure current? Again, in this example, still, like, how do you measure current through the load? Yeah.
You don't need 3 at 1 point. You don't need 2 necessarily. Is that what you're trying to get at?
One is in parallel, one is in series. Which one is in parallel?
This one's in series.
Ammeter works in series, voltmeter works in parallel. So if it's parallel connection, it's much easier for you to clip whatever that node, clip the other end of the voltmeter to that node you want to measure. But if you want to measure current, you need to break the original circuit, insert the ammeter there, and hope that your ammeter is not introducing too much of a resistance, which is typically much harder to do, especially when you're doing with neural tissue. So most commonly, we measure voltage in the nervous system. We're doing it electrically. Okay. But then there's a whole lot of jazz going on besides just electrical ways. There are also chemical ways. We can intervene with brain function. For example, psychiatric medicines, or whatever gets you high, which you should not be taking. those are usually analogs of neurotransmitters that is naturally being passed between neurons, but you can create analogs of those chemicals so that they mimic the function of those and give you that general state of being. But those medicines, they're notorious for not working too specifically because we don't understand brain function well enough to be specifically saying if I add the concentration of this particular neurotransmitter, what's going to happen. So it works over long periods of time and is usually non-specific. But also, the engineers and biochemists and neuroscientists have came up with ways to modify the neurons so that the chemical ways or electrical signals, they can be presented in biochemical ways. And from there, you can then present them in other forms, which is predominantly in optical forms. And that is thanks to the field of optogenetics. We can all see neural activities in real time. So your neurons don't naturally glow, but you can make them glow when they are excited. So there are all kinds of modifications people came up with, like calcium imaging, voltage imaging, fluorescent molecule tags, or optically stimulated ion channels, etc. All of these, they allow you to intervene with neurons just by shining a laser on them and then looking at them under a microscope. So that has greatly facilitated the field of neuroscience to help people understand how neurons work in tandem, how neural circuits work over long distances across the entire brain. But due to the risks of genetic engineering, these technologies are usually used on the academia and less used on human patients. Great. There's also, people may have also heard of MRIs used for brain imaging, and that's also actually one of very famous ways of imaging brain activities. Those are very well known for being non-invasive and can reach up to very high resolution. Well, and also there are people trying to stimulate brain activity using electrical fields, using magnetic fields. The mechanisms behind how you stimulate the brain using a magnetic field is not clear. As to how you measure them, that's much clearer. But whatever you're doing is just the main mechanism behind that is due to the conjugation of electric and magnetic fields. That if there's electrical activity, there has to be some kind of magnetic activity. If you intervene with one, the other has to change. If you measure one, you can also get the other. So that's just some basic understandings how magnetic fields can also help you understand the brain.
Awesome. Well, thanks so much, Brian, for going through all those details. And those details are really important to understand because a lot of times you might be working with this data or working with this technology, but you need to understand the biological basis and what these signals really mean. So, okay, so we're going to dive into some of the sensing modalities that are popularly used for BCIs, and here are the 3 criteria. And so I'll explain a little bit of this more later. But first is spatial resolution. Spatial resolution is how well you can accurately distinguish which parts of the brain are active during a particular neuroactivity segment. Next is temporal resolution, which is like when does the timing of neuroactivity happen. So like if I move my arm up and I'm recording my brain, what neuroactivity is correlated with me moving my arm up. And signal to noise ratio is really, really important because when you have these sensing modalities, they don't only record the signal you want, they also record a lot of noise and a lot of things that you don't want. So a lot of the things like power lines and whatnot, they get picked up by the sensor. So these are like kind of the 3 criteria we're going to be looking at. And okay, so if you go on to the next slide. So this is the first and probably a very, you guys might have seen this. So like if you see this patient, she had like this kind of thing sticking in on her head. And that's what's connected to what's called a microelectrode array. How many of you have seen the monkey Pong by Neuralink? So they likely use the microelectrode array to control the, it's this monkey, for those of you who haven't seen it, it's this monkey playing Pong by using thoughts and whatnot. So what a microelectrode array is, it's a high density electrode implanted on the surface of the brain. So when talking about the brain areas, it can be implanted on the motor cortex to detect muscle movement. And what it's able to do, it's able to not only record, but also stimulate on the neuron level. And so this is really important because this is like kind of the highest resolution you can get when it comes to neuroactivity on the neuron level. So it can identify which neurons or which group of neurons are firing. And you can imagine with that kind of accuracy, there's a lot of things you can do. So that's why that's popularly used. But this is an invasive sensing modality, so it needs surgery. Because you can't just like, I guess, it needs surgery to be implanted, and so it's only being used really for clinical purposes. But this high signal to noise ratio is kind of the main draw to it.
Do we have any volunteers?
What?
That's a joke.
The next one is also another invasive technology, electrocorticography, which also requires surgery. Essentially, it's this electrode pad that's put on the surface of the brain. And it's similar to microelectrode array, but except it's not actually piercing the surface of your brain, it's just being overlaid on the cortical surface. So this also has pretty good signal to noise ratio. It also can cover a lot more brain regions that the microelectrode array couldn't necessarily have. And so this paper, what did I say? So there's actually a lab at Hopkins here that uses electrocorticography, and what they do is they record patients who have locked-in syndrome. So these are patients who are fully conscious, can't speak, can't move or anything. And so what they do is they try to record their brain signals and try to decode their speech. And so if you guys were at the GVM a week ago, we showed a video of UCSF. What they did is they recorded brain signals and they had this avatar speaking. They use electrocorticography. And so a benefit of electrocorticography is signal to noise ratio, good signal to noise ratio, as well as covering a large areas of brain. But it requires surgery. So the next one is a non-invasive measure. So no surgery required to detect these signals. And I should mention, in addition to electrocorticography, electroencephalography, EEG, what they do is they record local field potentials. So that's what Brian was talking about. They don't record on the neuron level, they record the activity of a group of neurons. And so there's two different types of EEG. There's dry and wet electrodes. The main difference comes down to the signal quality and how much preparation is needed to actually put the EEG headset on. But it can range anything from this, as you guys, because this dude has like a lot of electrodes on, to like something as simple as like a headband. This obviously has a lot more channels and a lot more richer data, more complex data. This guy only has really channels on the kind of forehead area. So, but it's more accessible. Like you can wear it easily and whatnot. So we'll actually be using, so like Brian pointed out, this is an EEG headset with approximately 16 channels.
Exactly 16 channels.
Oh, okay, exactly 16 channels. And so those are dry electrodes. So you don't need any gel or anything to put that on your scalp. So that's a form of sensing. And so this next one isn't so much of a neurosignal sensor, but almost peripheral nerve sensor from the muscles. So when you flex your muscles, there's electricity that can be detected. And this is popularly used for things like prosthetic arms and things that you can control the drone with it. So we also have an EMG sensor there, just wrap it around.
You guys probably tried this over SIP.
Yeah, we had
haven't
it in
seen
SIF. So if you were by our booth, we kind of just showing it off. But yeah, so that detects muscle movement. Yeah. So that's kind of an overview of all the sensors that we'll be using and kind of sensors that that are existing in the field. There's also a lot more sensors that we cover, but those are just kind of like the highlights. So after you have all these sensors and you have your brain and you're recording all these sensors or recording all these signals, but those signals aren't always clean, as they say. So what you need to do is you need to figure out which signals are what you want and which signals you don't want. So one simple way to do this, and I'll kind of go through this briefly. If you're an electrical engineer major, you'll probably learn about this way more than I ever will. But so which is important. So there's certain, you can cut off the amount of signals at a certain frequency, so low pass. So a low pass filter will say, okay, give me a certain frequency, anything above that frequency, I want to cut off. So that's what you kind of see here. High pass is anything above a certain frequency I keep, anything below a certain frequency I cut off. Band pass is anything in a certain frequency, any signal with a certain frequency I keep, anything out of that interval I throw out. Band stop is kind of the inverse, and then notch filter is one that's like a signal at a certain frequency I throw out. And so you might be wondering like, okay, what's all this for? It's actually really, really important to get your data clean. Because in the next slide, we'll be talking about neural decoding. And with neural decoding, it's only, your algorithms are only gonna be as good as your data. So you need to really make sure your data is clean, or else your BCI isn't gonna really work. So when it comes to EEG, there's also a lot of artifacts. So one con about EEG is that the signal to noise ratio is relatively low. So the data that you're getting isn't very good necessarily. So for example, EEGs can detect eye blinks, and you don't necessarily want that. I mean, if you want to detect eye blinks, that's really good. But if you don't want to detect eye blinks, say you just want to assess like the cognitive function when they're doing a particular task, you need to correct for eye blinks, because you don't want to say, oh look, like activity is happening on when it's not really brain activities, it's muscle activity from the eye. So one way to do that is EOG artifact correction. So you can see here, so this is the clean EEG. This is the reference EOG, which is eye blinks. And when combined, when you're looking at the EEG without filtering out the eye blinks, you see these spikes, right? And those spikes are artifacts. And you don't want to keep that in your data once you're running your machine learning algorithms or doing anything like that. And so EEG also detects muscle movement, so when like you move your arm and whatnot. So you also need to correct for those. And again, this is really important because when we get to neural decoding, which is my personal favorite part, you need clean data to train your machine learning algorithms. And so this is kind of flowchart. So first we start off with our data. So that's again all we took from the sensors and the brain activity. And what we do, if you're familiar with machine learning, probably nothing around here is going to be super new, but this is machine learning applied to the context of brain-computer interface. So just like anything, we split it up in a training set and a testing set. So the training set is the amount of data that you're going to be using to help your machine learning model learn the patterns, learn how to say, okay, reading this activity, what output do I get? For example, like if I'm training a model to detect the different postures of a prosthetic arm, I want to see, okay, I'm recording my EMG activity, find an association or mathematical function that maps EMG activity to a certain hand grip. So you split this training set, so you have training data, which is like maybe EMG activity, EEG activity, and then you have labels, which could be like predicting whether I want to pinch, whether I want to grasp my hand, and whether I want to, I don't know, high five or something. And so you do that to train a machine learning model. And so you train your machine learning model, and then what you do is you also do the same thing for the test set. So you have a test data and then test labels. And then from here, you plug this test data into your machine learning model. So your machine learning model learn how to map data to labels, and it's going to make prediction from the test data. And then from there, you get a certain accuracy. Okay, how well were my predictions for the machine learning model? So this, I know this is not just like a bunch of blocks and whatnot, but behind the hood is a lot of math, a lot of data analysis, data cleaning and whatnot. And so this is kind of just the general framework of doing machine learning models. Yeah, so I'll dive into what two different types of problems when it comes to machine learning, classification and regression. Again, if you're familiar with ML, this isn't super new, but okay. So for classification, it's kind of what I was mentioning before. If you're like building a prosthetic arm and you want to classify different grips, you need to be able to classify, okay, is EMG activity related with one or the other? So that's what binary classification is when you only have two classes. So like I'll talk about some of the research that I did over the summer. So the research I did over the summer was analyzing neural data. So this neural data was also really interesting. The sensor we used was called stereo EEG. And stereo EEG is like this long strip of an electrode. And what it's done is implanted into the skull of or the brain of a subject with epilepsy. And so with this kind of sensor, what we did is we recorded neural activity of a participant playing a gambling game. And we wanted to see, okay, based on their neural activity, did they bet a high amount of money, which was $20, or a low amount of money, which was $5? And so that's a binary classification task. I have all this neural data, and I'm training a machine learning model, and I'm saying, okay, are they betting high or betting low? So there's two classes, and we try to differentiate between the two based on the neural data. Multi-class data is when you have more than two classes, like the prosthetic arm example that was. And so some example of algorithms, these might not mean a lot to you if you're not familiar with it, but logistic regression is one. Linear discriminant analysis is a type of model that's actually used by applied physics lab when controlling that really fancy robotic arm. They use LDA. to detect which grips from EMG activity. So the next kind of machine learning algorithm problem is regression, and this is kind of the problem we were trying to tackle in our project over the summer. So what regression is like, it's like predicting a continuous variable from input data. So an example in the context of maybe a prosthetic arm is controlling the movement velocity. You know, you can move your arm really fast or really slow, but like there's a variable in that. It might be like 2 meters per second, 5 meters per second, whatnot. And so that's kind of what you do. And so this tends to be a little bit not as common when it comes to brain-computer interface applications. Typically, it's classification, classifying different maybe intended words or intended arm grips. But regression is an important thing to be in general, and I feel like there could be a lot of advancements when it comes to regression-based neural decoding. And so these are some more algorithms. If you ever use like, I don't know how many of you are like physics lab or something, but like when you have to plot the like line of best fit, that's essentially to some degree you can like a regression problem. You have a set of data and you want to create a model or a mathematical model that says, okay, this is the trend I'm observing. So when you get a new set of data like this red dot right here, you say, okay, that's my predicted value is going to follow this trend, that's other data. So these are just kind of the two basic neural decoding algorithms. And again, this is just like a really surface level, but depending, this kind of supposed to introduce you to some of the areas that you may be interested in. And there's so much more to that.
Do you want to talk about like the sort of regression model that we were working on over the summer?
Yeah. Do you want to talk about it, Grace? You can talk about it. Okay. So what we were trying to do is so a lot of these classes, when it comes to prosthetics, one thing that's hard to control is the grip strength on those, or like how much you actually actuate the fingers of a prosthetic hand. Because a lot of times when I mention classification, it's like, okay, I'm gripping or I'm pinching, or like, I don't know, my hands are open, but the degree to which my hands are open, the degree to which I'm pinching, the degree to which I'm grasping my hand isn't necessarily controlled. And so that's a regression problem. Like maybe I want to grasp my hands maybe like 60% of it, or 60 degrees, and not like the full, like, I don't know how many degrees, but not the full clench. And so that's kind of what we were trying to tackle. And we were using EMG, an EMG sensor. So that's like detecting muscle activity. So that's kind of the project we were working on over the summer. Okay, this is also one of my favorite parts. I know I said neuro decoding was one of my favorite parts, but this is arguably, if not the more fancy part. So let's talk about the pipeline. So we have the brain recording the data with the sensors. We have filtering all the good, filtering out all the bad stuff, keeping the good stuff. Now we're training the machine learning model, and now we finally want to use the signals to then control a computer or control a machine interface. So I have a series of videos. So this is an example of a video, and this is
A quadcopter flies through a balloon ring. Cool, but what's the big deal? Well, look, Mom, no hands. There's no mouse or joystick here. It's all the power of thoughts.
Then the signal coming from his brain is being picked up by these sensors and then decoded and sent through a Wi-Fi system to control this flying quadcopter.
With support from the National Science Foundation, biomedical engineer Ben He and his team at the University of Minnesota created this brain-computer interface to help people with disabilities regain the ability to do everyday tasks.
The goal is eventually to make this technology to go to really help people, say, on a wheelchair with a variety of disability.
Professor He is still testing out the system with college students. Before maneuvering the quadcopter for real, they train for 10 to 20 hours using a virtual aircraft flying over a computer-generated campus.
We insert 2 different kinds of conductive gel that help us conduct a signal from his brain.
The interface is non-invasive, no implants, just an electroencephalography or EEG cap with 64 electrodes. When a participant thinks about a specific movement, neurons in the brain's motor cortex produce tiny electrical signals.
And the computer is going to read that digital signal and do all the processing and extract out the brain signal and control quadcopter.
Participants develop their own motor imagination, or simple mind tricks to help differentiate between moving the object up, down, right, and left.
So for me, catching a baseball is very different in my left hand from throwing a baseball in my right hand. So that really helps me kind of focus on one particular hand at a time to help move the helicopter to the right or the left.
The interface is designed to help with simple, everyday tasks like turning on a light switch. But Professor He and his team chose the quadcopter for the testing phase to keep participants challenged and eager to succeed.
The more fun they feel, more engaging, the better performance they can do.
Whether it's a wounded veteran or a stroke patient, the aim is independence. Eventually, he says this interface may help rewire brain circuits to bypass damaged areas.
You want to make a phone call, you want to turn on the TV, you want to switch the channel, you want to surf the internet. There's a huge societal and economic benefit to the society eventually with this research.
Harnessing brain power to help people with disabilities do for themselves. A high-flying idea. Just think about it. For Science Nation, I'm Miles O'Brien.
So what I hope you took away from that video is I hope you saw how elements that we talked about earlier in the lecture were also reinstated in that video. So could someone tell me what kind of EEG did they use? Wet. Yes, they used wet. So you saw that woman kind of squeezing that gel, and that's for the better signal to signal to noise ratio. And it's really interesting. So they first, before moving on to the quadcopter, what they did is they went to simulation first. And so this project that we're trying to do this semester of controlling a wheelchair with EEG and EMG, we're first going to run it through a simulation before we actually try to get a wheelchair, motorize it, and adapt it. So and that's really interesting as well. And I hope, my main goal is I hope some of the things that they said when it comes to brain regions and kind of the whole general framework. So this is someone controlling a computer, and this is interesting because this is the interesting part about this video is the sensor that they use. So I want you to keep an eye on the sensor.
Some conditions affecting the nerve cells in the body can result in disability. Spinal cord injury, stroke, limb amputation, and motor neuron disease, or ALS, may all cause paralysis, or even loss of the ability to speak. The stentrode is a neural interface designed to overcome paralysis by creating a digital bypass from brain to assistive device. An investigational device, the stentrode is inserted via a catheter into the jugular vein and manoeuvred into the brain without the need for open brain surgery. The sensors are built onto a self-expanding stent that engages into the wall of the vein and which is designed to maintain blood flow. Over time, cells may gradually grow over the sensors and incorporate them into the tissue. The sensors are placed immediately adjacent to the control center in the brain, known as the motor cortex. The patient may be paralyzed, but their motor control center can still be activated simply by thinking. The system is designed to transmit these brain signals out of the brain, out of the vein, and into a unit implanted under the skin in the chest. This unit is programmed to pick up brain signals continuously, and when connected to an external receiver, may send them to a computer. The command center in the brain is now directly connected to software, and the patient would attempt to train their brain for direct operating system control by thinking. Direct brain control of a mouse, a keyboard, exoskeletons, and even vehicles may become possible. Technology to restore independence. Synchron's neural interface technology, enabling people. Some conditions affecting.
This is really, really cool. And the reason why it's really, really cool is because they don't have to do open brain surgery. So it's a stentrode. So they access, I don't know if it's an artery or a vessel, but they access it to reach your brain.
Jugular vein.
Okay, jugular vein. And so that's really interesting. Elon Musk tried to buy out this company, interesting. So
because they got a FDA approval before you were.
Right. So this is really cool. And like I said before, okay, so another interesting thing is that they also are recording from the motor cortex. And so that's what you'll see a lot when it comes, if you ever read BCI papers, a lot of it is recording from the motor cortex. Because what they have to do is they have to think okay, move my arm left, move my arm right. They just have to think about it. And then from there, they can use machine learning algorithms or whatnot and nearly decode their motor intention. And then they can use that to control something like a computer cursor or a wheelchair. So that kind of framework you also see in it. So yeah, and then
some conditions affecting the.
So we talked a lot about like kind of the neural decoding and the machine effect and controlling it, but something that very last bubble on the very first slide that we showed, the feedback. So that's actually also a really important thing because a lot of limits when it comes to prosthetics or whatnot is the feedback. Because actually, like not a lot of people who are amputees like to use the EMG prosthetics. A lot of them also like the manual prosthetics, and so that's like less tech, but incorporates a lot of feedback for the user. Like you can physically feel how much you're gripping something. And so kind of the sensory feedback is really important. So what APL did is APL in this is like a couple weeks or something, they released news about adding the ability to detect heat using their prosthetic arm. And so that's what this is.
Back in 2005, when I was diagnosed with cancer, I had a special form of fibrosarcoma, and they did 5 surgeries trying to cut it out. I went from there to working with the modular prosthetic limb, and so our journey began.
APL has been really instrumental at developing these advanced prosthetic limbs. After amputation, the nerves that used to go to the hand, for example, are still there. We use these small devices that we place on the skin and try to figure out where are those nerves that we can activate now thermally to produce sensations of cooling in the missing hand.
The thermoelectric device that we have built is in contact with the phantom limb. So when the individual goes and uses a prosthetic arm, there is a thermal sensor that senses the temperature of the object that's being touched and transmits a signal to our device and immediately sends a sensation to the phantom hand.
We'd already found out motor control were there, but to be able to reach back here, touch something, and know whether it's something cold or whether it's just room temperature or whatever, that right there you go. That's where it's at.
One thing that's really unique about the thin film thermoelectric cooling technology that we're able to leverage is that it's extremely fast.
Biological speed is approximately 1/3 of a second. The devices that are available in the market operate at about 3 seconds, so it's almost like 10 times slower. We don't go and touch things for a long time. We touch quickly, we want to know what it is. The work that we're doing at APL is to create unique materials that overcome some of the limitations.
It's really amazing being able to work on such exciting technologies, but it really wouldn't be possible without all the wonderful participants. They're the true pioneers.
To actually have this device being put on a human being, that's a huge blessing.
Johns Hopkins Applied Physics Lab. These people right here are so daggone smart they can do anything with anything.
Yeah, I mean, that's really important. It's this BCI, you want the human in the loop, right? You want to have that user feedback so that user experience is a lot more better. And yeah, and I think that's all when it comes to the presentation. So thanks so much for coming out here. I know the semester is kicking in and everybody's got midterms, everybody's got homework, everybody's tired, like trust me too. But thanks so much for taking the time to come out here and learn a little bit more about BCI. So the next workshop we'll have is next week. And so this will be an EMG workshop. We're gonna try our best to make it as interactive as possible. We don't have a ton of supplies, but that shouldn't deter you from coming if you're interested in participating in this. This would be more of like a hands-on. So this is a lot of lectures and whatnot. But from now on, it's gonna be hands-on workshop. So yeah, thank you so much. So keep that in your calendar, same time, same place. Yeah. If you have any questions, feel free to ask. If you need to leave, feel free to leave.
Oh, by the way, for anyone that came late.
Alright. We'll try to do our best to get more chairs in the room so people aren't sitting on the floor. We're really sorry about that.
So for anyone that just came in, if you didn't have a chance to scan this yet, please scan this code so that we know you came to the lecture. You have any questions for the audience? Look ahead into the EMG workshop. That is exactly what we'll be working with. these are literally just wires, conducting wires that stick on the surface, like that's close to your muscle. So that is electromyography. And then you have that information passed on to this piece of chip. That's a modified version of Arduino. It's called Cdrino. But practically, you can code it in the same way as you code Arduino. So the signals get picked up here. It's sent here. You can then hook it up to the computer to program it and to actuate it. Say, I haven't plugged it in yet, but you can use that and then say, use your muscles, run the code here, and then you can process the outputs to control a little servo motor. It's a very basic example of how you want to use electromyography for controlling something mechanical. Okay. If that sounds interesting, please do come.
And we're gonna prepare like a document, also like the folder of everything you need to download on your computer before coming to all the workshops.
Yeah.
So that like once you download that one file, you should have everything ready for all of the workshops. And we're gonna get that out as soon as possible. Also with like instructions for downloading.
Questions? Well, otherwise, repeat this.